Hi, my name is David, and I'm a software engineer at Facebook. And today I'll be talking about Taiji, our system for managing user traffic at the edge. So Facebook operates a geo-distributed infrastructure with dozens of data centers around the world. And when operating our infrastructure, we care a lot about efficiently utilizing our data centers and also providing our users with the best experience. Routing user traffic has a big effect on both of these, and to show this, I'll first explain how users are routed to our data centers. When users access Facebook.com from their device, they're first routed to a nearby edge node, or point of presence. Edge nodes are small data centers that Facebook places close to our users for latency and caching benefits. And so if the request is for static content, then the request will be served out of the edge by our CDN. Now, if the request is for dynamic content like a news feed, the request must be routed to a data center for processing by a web server. And depending on the request, the web server may need to call into several backend services for further processing. When done, a response is returned to the user. So the reality is that Facebook has lots of these edge nodes routing to lots of our data centers. And in this talk, I'll be going over how we decide to route users from these edge nodes to our data centers. There are three things we care about when routing user traffic. The first is in efficiently utilizing our data centers. We don't want to strand or overload any of our data center capacity. So for example, let's say we route a bunch of our users to the same data center. If we do this, it may end up overloading the data center because we send it too much traffic. The second thing we care about is routing users to nearby data centers to ensure we're providing a good user experience. So for example, we could route users to faraway data centers and satisfy our first concern of efficiently utilizing our data centers. But this would provide a bad user experience. So instead, we'd like to route them to nearby data centers. And our last concern is in efficiently utilizing our caches. Facebook infrastructure has several layers of caching, and we want to ensure that we're effectively utilizing it. We achieve this by consistently routing users to the same data center. So this means that subsequent requests can leverage previously cached data. We took it another step further, though, and we noticed our users are socially connected. So for example, we have a group of users who are all friends. One friend makes a post, and both of the other friends will see the same post in their newsfeed. So what we realized is if we route all of these users to the same data center, we can better leverage the cache because they're all fetching the same content. So accomplishing these three goals is challenging because our site is constantly changing. First, user demand is growing, and growth varies by geographical regions. Second, our data centers are constantly changing, and they could be upgrading, refreshing, or decommissioning hardware, thus changing the capabilities of the data center. And we also build new data centers. And lastly, failures are very common at our scale, from losing machines to whole data centers. And when a data center goes offline, we need to reroute traffic to other data centers. So far, I've only shown our routing dynamics with simple examples, but here's a graph of user demand to one of our edge nodes to better show the complexity. This graph shows the requests per second to an edge node, and what you'll notice is at the peak, it's serving up to 3 million requests per second, and at trough, it's serving about 300,000. So that's already like a 10x difference. In addition, here's traffic at two more edge nodes, and what you'll notice here is that the peak demand can occur at different times of the day based on geography. So the reality of our infrastructure is that we have lots of these edge nodes, and their traffic changes greatly based on geography and also the time of day. So for the first decade of Facebook's existence, we survived with a static mapping of edge node traffic to data centers. So what that would look like is, for example, an edge node would be sending 50% of its traffic to each of its nearby data centers. And so this static mapping strategy started to break down in 2015, which I'll show you next. This is a graph of the utilization of our data centers over a day in 2015, where the x-axis is the hour of the day and the y-axis is the data center utilization. What you'll notice is that at hour 6, several data centers are underutilized at 10%, while others run at 60%. And so this is inefficient and could be better utilized by balancing traffic to them. We also have the concept of a danger zone, where we start to see our systems queuing and violating our SLAs. And so at hour 19, a couple data centers are running into this danger zone. So the challenges of managing site traffic came to a head in the fall of 2015 when site operators had to tune the static mapping daily to ensure the site could run smoothly. And so that we found that the static routing is very inefficient, error-prone, and time-consuming. So we took our experience manually managing user traffic and designed Taiji. Taiji is our system for managing edge to data center traffic. Taiji runs continuously, shifting traffic to react to site dynamics like user demand, capacity changes, and failures. Taiji is able to balance the data center utilization while minimizing network latency. And it also leverages user connections for cache efficiency, reducing reads to our backend storage by 17%. And lastly, Taiji has been running in production for over 4 years now. For the rest of this talk, I'll be going over an overview of Taiji, specifically about how we decide the traffic allocation and user routing problems, and then I'll present our evaluation of Taiji. So there are 2 fundamental questions. The first is how much traffic to allocate from each edge node to each data center, and this has an impact on balancing the utilization and minimizing the network latency. The second question is how to route the users, and as discussed before, this affects cache efficiency. We answer both of these questions with Taiji. So I'll go into the details of each of these components, but first here's a high-level overview of how these 2 components work. The traffic allocator takes as input a routing policy configuration that specifies whether to prefer balancing utilization or network latency. The traffic allocator will output a traffic allocation, which is a percentage breakdown of how much traffic to send from each edge node to each data center. Connection-aware routing will take this traffic allocation as input and decide how to map users to data centers. Here, we have connected users routed together to improve the cache efficiency. So connection-aware routing will output a mapping of users to data centers, which is distributed to our edge nodes, and this will update the routing accordingly. So now I'll explain how we built each component, starting with the traffic allocator. The traffic allocator's goal is to decide the traffic allocation based on the utilization and network latency. So now I'll go into the details of what this problem looks like. In this example, we want to balance the utilization and be latency aware. So the boxes here represent the requests from the edge node and the data center capacity, and each box represents 1 request per second. Also, this center data center is placed further away to represent that it has higher network latency. So first, Taiji needs to decide how to allocate traffic such that it can achieve a balanced utilization. And we do this by computing a target average utilization by summing up the total demand and dividing it by the total capacity. By doing this, we'll see that in this example, each data center should be about 50% utilized. So next, Taiji needs to decide how to allocate the traffic to optimize for the network latency. And the strategy here is to send as much traffic from an edge node to its closest data center without exceeding this target utilization. So in this example, what will end up happening is that each edge node will send 3 requests to its closest data center and 1 to the further away data center. So what you'll notice is that in this routing policy, it trades off in the network latency for balanced utilization. And we designed Taiji to be customizable so that service owners can configure how to trade off these 2 goals in a way that's best for their service. When we first implemented the traffic allocator, we only had our main web service use case. So we built a closed form solver to support the routing policy of balancing utilization while minimizing the network latency. Over time, Facebook's products grew, and different services had different routing policy requirements. For example, a latency-sensitive service wanted a latency-optimal routing policy, while another service wanted a simple balancing policy. So we implemented each of these policies as separate closed-form solvers, but this quickly became hard to manage and time-consuming. Also, debugging these different implementations in production is challenging, and there would be duplicated effort when making fixes. So instead, we generalized the traffic allocation problem as a constraint satisfaction problem, and we use a constraint solver to compute the optimal traffic allocation. This design enables service owners to experiment with different routing policies to find what works best for their service. And in addition, with this design, we're able to unify our closed-form solvers and reduce the operational complexity of the traffic allocator. Next, I'll be going over the second component of Taiji, the connection-aware routing. And so the goal of connection-aware routing is to route connected users to the same data center while respecting the traffic allocation. Our initial approach was to group connected users into 21K fixed-size buckets and route at the granularity of these buckets. But there's a downside to this approach, which is choosing the bucket size. A small bucket size where each user would be in their own bucket would provide very fine-grained routing, but this would break up social groups and lose out on cache efficiency. On the other hand, a larger bucket size would put more of these users together, but this would be at the expense of routing granularity. So our approach is to create fine-grained buckets for the routing accuracy, but also to route groups of buckets, of related buckets, to achieve higher cache efficiency. So how do we know which buckets are related? We do this by partitioning our users into a hierarchical structure to encode how buckets are related. So we create this structure by first taking the set of all of our users and running a balanced partitioning algorithm to create two subgroups. And these two subgroups are created in a way that it minimizes the connections between them. We run this algorithm recursively on each of these nodes until we create this hierarchical structure. So the key thing to note about this structure is that the leaf nodes are the buckets, and the inner nodes represent the subtrees of these user buckets. And we run this algorithm, the balanced partitioning, until the user buckets each contain about 0.01% of all of our users to achieve fine granularity in routing. With this grouping of users into the hierarchy of buckets, we need to solve the problem of how to assign the user buckets to the data centers. And we do this with stable segment assignment. The intuition behind stable segment assignment is to try to assign large subtrees of buckets together while splitting a few to enable the fine granularity in routing that we need. And you can read the details of this algorithm in our paper. So to recap, Taiji solves the problem of how to route users from the edge to our data centers. And it does this in two parts. The traffic allocator decides a traffic allocation while balancing the utilization and minimizing the network latency, while connection-aware routing optimizes for cache efficiency by routing connected users together. So we evaluate Taiji on exactly these three areas. Specifically, we ask these three questions. How well can Taiji balance the utilization? How optimal is the network latency? And does connection-aware routing improve cache efficiency? So I'll start by going over how well Taiji can balance our utilization. Here's the graph from the beginning of the presentation with the utilization of our data centers in 2015. And here's the graph of our data center utilization now, after rolling out Taiji. As you see, Taiji is able to effectively load balance the utilization. And what we found is that for a stateless service, Taiji is able to balance the service's utilization to within 3%, 80% of the time. The divergence is due to continuous deployment, which are the spikes you see on this graph. And continuous deployment is this process that continuously takes down machines to deploy new code on them. And this can cause some imbalance. But even with continuous deployment, Taiji is able to keep the data centers well balanced. You can also see here there's a drain and undrain event, which was necessary to mitigate a site issue. And Taiji is able to react to this event and balance the utilization. For evaluating network latency, we want to see that Taiji is actually able to improve the network latency. So we compare the network latency of Taiji's routing decisions with three different routing policies. The first is a random routing. The second is a static mapping that we had in 2015, which was hand-tuned by a human for optimal latency. And the third is a theoretical lower bound. And this theoretical lower bound is simulated by taking the traffic from each edge node and routing it to its closest data center, assuming that data center has infinite capacity. So the thing to note about this theoretical lower bound is that it can't be achieved by routing alone and would require actually provisioning more capacity. So Taiji is able to achieve a better network latency than the random and static mapping. And also Taiji is able to stay within 30 milliseconds of this theoretical lower bound throughout the day, which we find tolerable for this application. The key thing to note is that we're able to actually improve the network latency over this static mapping that was created by a human trying to optimize for latency. And it's doing this while balancing the utilization. So Taiji is able to achieve the best of both worlds, of improving the safety of the site and also minimizing the network latency. Finally, we evaluate connection-aware routing on the effectiveness in improving cache efficiency. And while I could show some graphs on the cache improvement, we found it most meaningful to show data on the reduction of reads to our backend storage, because this translates into a reduction in backend capacity. So this figure shows the amount of queries per second to our backend storage over time. And after the rollout of connection-aware routing, we found that we reduced the reads to our backend by 17%. So before I conclude, let me go over two limitations of Taiji. The first is that Taiji only considers the edge to data center latency. However, service owners care a lot about the end-to-end latency. And what we found is that these can sometimes be at odds with each other. For example, a latency optimal routing policy can actually run a data center at higher utilization, and this could cause it to experience queuing, and this may end up increasing the end-to-end latency. In this case, balancing the utilization would actually achieve a better end-to-end latency. So we rely on service owners to understand this about their systems and to configure Taiji to account for this. The second is that Taiji only considers the front-end utilization and doesn't consider back-end utilization. And we solve this problem by running continuous load tests to verify back-end capacity is sized properly. So to conclude, I present our system Taiji that's been running in production for over 4 years and reacts to the daily site dynamics. Taiji supports flexible configuration so that services can make their own decisions about trading off a balanced utilization and minimizing network latency. And finally, Taiji routes connected users, which reduces the reads to our backend storage by 17%. So thanks for listening to my talk, and now I'll be taking questions.
Interesting talk. Xiao Zhang from Google. You showed two slides compare the utilization from 2015 and 2019. Is that a data center CPU utilization or memory utilization or bandwidth utilization? What resources you are comparing?
Great question. So you're asking what is the actual metric we end up using to measure the utilization?
Yes.
So for this service, we have this custom metric that's measuring essentially like the CPU. It's measuring the throughput of CPU for those machines, for that data center. Sorry.
Okay, and you empirically decide 80% is the dangerous zone. Is there any heuristic for that?
Sorry, can you repeat the question?
One slide you showed that 80% of utilization is a dangerous zone. Do you have an empirical reason to define this threshold?
Yes, it's the point at which when we run our services at like higher than that, we do observe there's queuing effects and there will start to be delays in the processing of the requests.
Okay, thank you.
Mm-hmm.
Hi, Brad Karp, UCL. I enjoyed your talk. My question is, if I understood the description of connection placement correctly, I think you're assuming that you don't run out of capacity on any of the edge to data center links, that you assume that there's no constraint on the edge to data center links, that the balancing you're doing looks at balancing in the data center.
Mm-hmm.
My question is, does this just mean that your wide area links must be over-provisioned because you're not thinking at all about getting close to full utilization on them? So why is it not necessary to consider that constraint?
Okay, great question. So as I understand it, you're basically asking like, why do we not consider network capacity in Taiji?
Yeah, given the cost of network
Yes.
links, yeah.
Yeah, so at Facebook, when we do network planning, we plan our links to survive the worst case scenario. And then we run these large scale tests to verify that it's planned correctly, which are like load tests on our data centers and also DIRT tests, which I believe are like disaster readiness tests. So when we run these tests and compare it to the amount of traffic we see that Taiji's managing, we see that Taiji's not able to actually stress the network past those limits.
So you're saying the links are over-provisioned, essentially?
It's not that they're over-provisioned, but they're provisioned for a disaster scenario. And so Taiji is operating within those limits.
I see. Thank you.
Mm-hmm.
Hi, Marius from EBFL. I assume you make the assumption that the majority of your services are stateless, so any data center can serve any user, and based on that, you can control the data center utilization. So is this a safe assumption to make, and how can you so massively affect the utilization of the data center just by playing around with the stateless servers?
So your question is it a fair assumption to assume we can move the user traffic to our different data centers? And what was the second part?
Is it a safe assumption to make that the majority of your services will be stateless and that there will be no data center local state per user that might be also necessary to move once you move the user?
Mm-hmm. Okay. So at Facebook, our data centers are designed in a way that any of them could serve this traffic, at least for the front-end services. And what we observe is that for many of our front-end services, this assumption actually does hold. Yeah.
Thank you.
Okay. Thank you very much.